In this video, we're going to talk about the basic structure and vocabulary describing the sun. Now, when you look at the sun in visible light, you'll see something like this. Now, quick warning, don't go out and stare at the sun. You need special filters to block out most of the light. But if you have one of those special filters and you look through it, just one that blocks light but doesn't change the color or anything, you will see this basically a yellow ball. And but there may be blotches, and these are called sunspots. Just to put a sense of scale, the sun is about 1.4 million kilometers in diameter. That's about 110 times the Earth's diameter. And I put a blue dot here to the same scale, showing you the size of the planet Earth in comparison. And the sun rotates. It rotates on its axis, and we can see that because the sunspots go around. And so that tells us that it's a rotating ball. And one thing that's weird, though, unlike the Earth, the sunspots, the time it takes for the sun to rotate is different for different latitudes, basically, on the sun. Now, on the Earth, the equator goes around in 23 hours, 56 minutes, 360 degrees. Well, so does Canada. Goes around in 23 hours and 56 minutes, 360 degrees, turn, a sidereal day. And that's because the Earth is a solid object. If it turns, it all turns with the same rotational period. Not so with a big ball of gas, and the rotation period varies from 25 days near the equator to 35 days near the poles. We call that differential rotation to make it sound fancy. What is the sun made out of? Primarily hydrogen. And now this table is listing percentages by both volume and by mass. And when we say by volume, that essentially means by numbers. How many? So out of 100 nuclei on the sun, almost 91 of them are going to be hydrogen nuclei, with about 9 of them being helium, and those rounded numbers, and very, very small numbers of everything else. And now you can also count it by mass. Now hydrogen is the least. It's the lightest of the elements, the nucleus just being a single proton. So by mass, it's not the same percentage, but it's still, even by mass, the highest percentage out of all of them. So whether you're counting by numbers or / volume or by mass, hydrogen is the most abundant element in the sun, with helium being the second most abundant, and then the other things listed there being very small amounts in comparison. Now this diagram is showing you a cross-section of the sun with a lot of that important vocabulary. And so I'm just going to go through the vocabulary very quickly here, and then we will talk about a little bit more detail. But the very center of the sun is called the core. It's where the energy is actually created in the sun by nuclear reactions. And then outside the core, we have what's called the radiative zone. And then outside the radiative zone, we have what's called the convective zone. And then at the top of the convective zone, we have the surface of the sun, which we call the photosphere. So whenever I say surface of the sun, I'm referring to the photosphere. Because when you look at the sun, again, through a safety filter, that's the ball you're going to see, is the photosphere. And what the photosphere is, that's just the point at which the gas becomes transparent. It's all gas. There's no solid surface. It's just the photosphere is the point at which the gas becomes opaque going in, or becomes transparent for things coming out. It's the dividing line between opaque and transparent. And so that's the surface of the sun as we see it. And sunspots are basically at the photosphere or a little bit above. The chromosphere is a layer just above the photosphere. And then above the chromosphere is the corona, what I usually describe as the atmosphere of the sun. The in terms of, let me just say a few things about the chromosphere and the corona, because they're not in the next slide. Temperatures in the corona, the temperature of the gas, it's a very, very thin gas, but the temperatures can actually get up to about 2 million Kelvin, involving the magnetic field somehow pumping energy into those particles out in the corona. The chromosphere gets up to about 20,000 Kelvin, which is about 3 times hotter than the photosphere. The photosphere is about 5,800 Kelvin, is the temperature of the surface of the sun. A few other vocabulary things here. You can have prominences, these big jets of gas that come off the surface of the sun, and flares. These are spots that are hotter than the surroundings. And then in the corona, in some places, you will have a coronal hole, where just the density of the corona is less than typical. So here's another diagram, a little bit less vocabulary on this one. And the core, like I said, that's where the energy is being released through nuclear fusion reactions. We'll talk in more detail about that. But the temperature core is about almost 16 million Kelvin, almost 16 million Kelvin. And so that's where the energy is being created, and the energy is trying to get out. And there are different ways that energy can move. And one of those ways is through radiation. Another one of those ways is through convection. So radiation is literally electromagnetic waves. That we've talked about electromagnetic waves. And the core is so hot. Remember Wien's law? The hotter something is, the shorter the wavelength of light that it emits. Well, the core is so hot that it's emitting primarily gamma rays. And so you've got gamma rays being radiated by the core, and it's trying to get out. And you might think, well, gamma rays, they should be traveling at the speed of light. That 3 times 10 to the 5, 300,000 kilometers per second. But that's in space, that's in a vacuum. Inside this material, it's kind of trapped. It's trying to get through this plasma, this ionized gas, where you have the protons and the electrons. A plasma is where it's so hot that they don't form atoms, they're separate. So you got all these charged particles. Light's trying to go through the charged particles, and it can't. It gets blocked. It gets absorbed and re-radiated. And so think about like if you were trying to cross a big, big room, and it's a mosh pit. It's a mosh pit, and you've got 1,000 people packed shoulder to shoulder and dancing and just bouncing off of each other, and you want to go to the far side of the room. You're just trying to walk across the room, and let's say you're trying to go to the bathroom. You really have to go to the bathroom. You're trying to make a beeline straight across, but you're going through this mosh pit, and you hit somebody, they knock you, and you go every which way. So the gamma rays are trying to go through a mosh pit of protons and electrons trying to get out into space. And so this is the radiative zone, and it actually takes, for a given gamma ray, so to speak, or the energy from a gamma ray to make its way out, actually takes a couple 100,000 years, believe it or not, to cross this distance. And but when you reach the edge of the radiative zone, that is where the density has changed enough. The density has dropped enough, and the temperature gradient, that is the rate of change of the temperature, has changed to just the right value that the gas starts to convect. And convection is this swirling motion like on a pot of hot water on a stove, where the water at the bottom is hot and it rises because it's less dense, and the water at the top has cooled and it falls, and you get the circulation. And so that's what's happening in the convective zone. And the energy there can get out much from there, is carried, it's kind of like an elevator, carries the hot material up. And when the material reaches the photosphere, it is free to radiate it out into space, because the photosphere is where the material, the density has dropped enough that it becomes transparent. And the density, and also it's no longer ionized at the surface. You're going to have it's no longer a plasma right there at the surface. So it becomes transparent, and the light can escape out into space, and that is the surface of the sun as we see it. So that's a quick introduction to the parts of the sun. This slide, don't freak out, everything I just told you is on this slide, so I'd like you to hit pause here and read this. And if you need to fill in your notes, go ahead. But everything that I've said everything here I've already said. So hit pause, and then when you're ready, move on. So the sun is made out of gas. And through most of the sun, it's plasma. That means it's an ionized gas. It's so hot that the electrons are stripped away from the nuclei. But saying that it's a gas, you might think, oh, well, I know what a gas is, like air is a gas. But what holds the sun together is the same thing that holds planets together, gravity. All material, all matter has gravity. And when you get lots of it, the gravity can actually force the object to be spherical. And the sun is so much more massive than the Earth. I haven't shared this number with you. It's 300,000 times the mass of the Earth. So 300,000 times the mass of the Earth is going to create a lot of gravity. And in the very, very center of the sun, the material is so compressed, so squeezed by that gravity, that the density is over 100 grams per cubic centimeter. Now let me introduce this graph here a little bit. The vertical axis is density in grams per cubic centimeter. And notice that it's a logarithmic scale. Okay, so this is 10 to the minus 4, 0.0001 grams per cubic centimeter. Air is about 10 to the minus 3, 0.001 grams per cubic centimeter. Air here on the Earth. Water is 10 to the 0, or 1 gram per cubic centimeter. And gold is like 13 grams per cubic centimeter, something about there. And that's one of the more denser. Lead and gold are kind of the most, not the most, but among the most dense materials on the periodic table. So this is a logarithmic scale. Here's water at 1, this is 10, this is 100. Now the horizontal axis is a linear scale, and it's radius from the center. So the center of the sun is here on the left, the surface of the sun is on the right. And so in the very center, you have, it's in the neighborhood of 200 grams per cubic centimeter as the density of that gas in the center of the sun. And then it drops, it drops, it drops. Keep in mind, this is a logarithmic scale, so this is actually quite a big change going from 1 or 200 down here to 10. But at about a little bit inside the edge of the core is where the density is only the density of gold, and you get out to about 55 or 60% of the way out is where the density has dropped to the density of water. And then as in the convective zone, as we near the surface, the photosphere, the surface, the density does start to drop off dramatically. And so reaches very, very small values at the surface, at the photosphere. So I don't want you to think that there is a solid surface that you can stand on. It is gas, but it's very, very dense gas on the interior. This is a very similar graph. The horizontal axis is radius from the center, but the vertical axis is now temperature. And I had mentioned it's almost 16 million Kelvin in the very center. So 10 to the 7 is 10 million. Okay, 10 to the 6 is 1 million, so 10 to the 7 is 10 million. So this is about 16 million Kelvin. And again, the temperature drops, but then drops dramatically in the convective zone as you reach the surface. Notice that the line here ends at the surface at a little bit under 6,000. So this is 10 to the 3, that's 1,000. So 2, 3, 4, 5, 6, and then just going over here, 2, 3, 4, 5, and so between the 5,000 and the 6,000 is where the graph stops there at the surface of the sun, at the photosphere. Just a couple other things. Pretty picture of the corona. The corona is there all the time. We don't see it normally because, of course, the bright daytime sky. And even if we didn't have an atmosphere, or even if you were an astronaut in space and you looked at the sun, you would be dazzled by the photosphere. It's just so bright that it would be very difficult to see the corona, even if you didn't have the blue sky, the atmosphere. And so we can put something in front of the sun, though, to block the light. And nature does that for us during a total solar eclipse. And so during a total solar eclipse, we can see the corona. And one thing I just want to point out, look how big it is compared to the sun. Now I know this is the moon you're looking at, but it's the same angular size as the sun, or just a smidgen bigger. And so look how big the corona is. The Earth's atmosphere is thin compared to the body of the Earth, but the corona is actually quite large. And this is just a close-up of that same image showing all that interesting structure in the inner parts of the corona. And this is related to the magnetic field of the sun that we're going to talk about in more detail later. Now I've got this little video clip that I want to show you. This was taken by some satellites that NASA has. NASA has a number of probes that are dedicated to just looking at the sun all the time. And one thing that happens is what are called coronal mass ejections. These are when the sun ejects just big blobs of material out into space, and not necessarily even to come back, just forever shooting out into space. So let me start the video clip. It's got some funky music with it. And this is kind of a close-up. Now these are taken through special filters. The hydrogen alpha line that we have mentioned in past, it's that hydrogen line that radiates at 656 nanometers. So you can put a filter in that lets through just that light and allows you to see all this contrast that you wouldn't see just with, broad spectrum white light. Okay, now a broader view, zoomed out. Keep in mind these things shooting off from the sun are far larger than the planet Earth. Now this is an even broader view. The white circle here represents the diameter of the sun. The red circle is actually a device inside the telescope that is blocking the glare even from the inner corona. And then we've got, this is kind of a merge of several different cameras and filters that allow you to see those very, very faint gases as they travel outwards. The green here is just a different filter in a different camera, and they kind of patch these together. Now these coronal mass ejections that just continue outward, they can, if they're headed towards the Earth, they can interact with the Earth's magnetosphere, interact with the Earth's atmosphere, and they can create auroras. So I couldn't, I just felt compelled to finish this video with a pretty picture of an aurora. So this is caused by material from the sun being channeled by the Earth's magnetic field into the polar regions of the Earth. And so that's just a pretty still picture. And this is actually a little, just a quick little movie clip from the International Space Station showing you an active aurora. And so that wraps up this video, quick overview of the sun.